16 nodes and 16 tropes. And the remaining one, so we have 32 involutions. So the remaining 16 involutions, switches, sorry, taking the minimal resolution, here we have 16 minus 2 curve. Also, proper transform, we have another 16 minus 2 curve. All of them are lines here. So totally 32 lines. And 16 translations preserves each family of lines. But the remaining 16 evolution switches these two families of lines to families of 16 lines. Okay. Also, Klein pointed out, so we have a 16 nodes, but we take a projection from a node. Then, okay, so we take a node on the Kummer cortex, then take a projection. So,
switch the two families of 6 lines are totally exchanged.
Yes, complete, yeah. This is a non-symplectic, and also related to dual. We have a dual Kummer. That is projectly isomorphic to original Kummer. So that is and consider the line through a node. Then this is the cortex, and this is the one intersection number is 2. So additionally, we have a 2 point. And switching this one, we get involutions of Kummer cortex. Okay, so totally we have 16 nodes, so 16 involutions. And also dually, we get another 16 involutions. Okay? So Klein knew these birational involutions. And he asked so other involutions, and then Hutchinson 99. No. He gave 2 types of involutions, 60 involutions, associated to 60 Geppel tetrad, and also 192 involutions associated to 192 Weber hexad. I don't explain these things, but anyway, these are set. For example, Geppel tetrad means a set of 4 nodes. Okay, and with respect to this set, Kummer cortex can be written as another cortex model, also here. And some Cremona involution acts, naturally acts, so we get an involution of this type. Okay, and this is also the 19th century. And then maybe people forgot. And, sorry, people forgot. And Young Hek Kun, at the end of the 20th century, he discovered a new 192 automorphisms. Okay. But at that time, he didn't know Hutchinson's involutions, 192. So he claimed the new. And then I proved. So G's automorphisms generate automorphism group for Picard general Kummer surface. So, but later, Ohashi-san pointed out existence of this automorphism. And this is natural. So now we don't need Kummer's automorphism anyway. Okay. But his automorphism has an infinite order. So in this sense, I think it's interesting. Okay. Also, Kummer and I also calculated automorphism group, this type. These are elliptical. Okay. So, this is a story over the complex numbers. Okay. Okay. And I think positive characters different from 2. I think this method works well, I think. But what happened? So my motivation is what happened in characteristic 2. Some of you heard my talks on Kummer in characteristic 2, maybe many times. Anyway, so characteristic 2 case. No, not new section. So this case, what happened? So I think Shioda. Picard general, so the possibly minimum. Yeah, so this case is the Picard number is 17, hyperplane section and 16 disjoint -2 curves. Okay. Okay. And Shioda and Katsura pointed out, so this was Kummer quartic. So the notation is not so better, but so divided by inversion or product type, they have there are 3 cases of occur, different from 2. Quotient has only 16 nodes, but characteristic 2, 3 cases occur. So this case D4 singularity, or 2D8, or elliptic singularity. So this case, if so two torsion group is G over 2G 2, and this is the same G over 2G, or only 0, only 1. So this number is called the P rank, but it's okay. Yeah. In my talk, this is enough. Okay, so situation is different over the complex number. So what happens? This is my motivation. Okay. And the main theorem is very similarly. So we can give a generator of this automorphism group in characteristic 2. Okay. This is my introduction. Okay. It's okay? No questions? Understandable? Sorry. And now I come to the lattice theory. Next section. So anyway, so our automorphism group, we have a natural map. This is the Picard lattice, and this is the orthogonal group. And this is divided by plus minus 1, and while group or reflection group. This is a reflection group. So the subgroup group generated by minus 2 reflections. And we have a natural map here. But it's known. This is finite kernel and co-kernel. Okay. And this is nothing but symmetry ample cone. So ample cone is a fundamental domain of this reflection group. But Kummer surface has infinitely many automorphisms. So the ample cone has infinitely many faces. So it's difficult, it's impossible to find its symmetry. So in this section, I want to explain how to find fundamental domain of the automorphism group. So we can use a Leech lattice introduced by Mukai. Okay. So, and the idea is already Mukai-san talked. So our Picard lattice sitting, this is in his terminology, like this. This is a even unimodular lattice, even unimodular negative definite. No. Signature 125. And U is a hyperbolic plane. And this is a Leech lattice. This is an even unimodular negative definite, rank 24, and not contain minus 2 element, minus 2. Okay. And my strategy is to get a primitive embedding. And here, so the Conway found a fundamental domain of the reflection group of this lattice. So we can restrict to this fundamental domain. We get a fundamental domain of the automorphism group. This is a simple story. Yeah. Okay, so maybe, sorry. This is a even unimodular lattice, negative definite, rank 24 without minus 2. Also, maybe there are 24 isomorphism classes of even unimodular negative definite lattice of rank 24. This is called Niemeyer. And its isomorphism class is determined by its root sublattice. So, for example, we write EH3. This is the orthogonal direct sum of 3EH. This is unimodular. Also, D24. So the Niemeyer lattice, whose root lattice is D24. And finally, Leech lattice is nothing but empty root lattice. Okay. And then, okay. So I fix fixed decomposition, and I use this terminology. So lambda is sitting lambda, and mn are integer, and the norm is given by. Also, I take some special vector, 1, 0, 0. So this is called a wild vector. And I remark perpendicular to rho. This lattice doesn't contain any minus 2 because if perpendicular to rho means n is 0. So the square is lambda square. But this lattice doesn't contain the minus 2. So, okay. And one more definition. So I define, so the each root. So R is called a each root if R is a root minus 2 and intersection number with rho is 1, smallest one. And I denote the delta. This is a set of each roots. And Conway's theorem is delta is a simple, nothing but a simple root for the theorem of Conway. So let's see the vector in the positive cone plus this is a positive cone. This is a hyperbolic space, so we have a two connected components, but I take one. Then define by this inequality, so for any delta. And then Conway's theorem is C is a fundamental domain of reflection group minus 2 reflection with respect to the action on this positive cone. This is his theorem. So this is a fundamental domain, but the each root, set of each root is infinite. Sorry, this bisexually correspond to each lattice. For example, if you take lambda, then this n should be 1. And here is a minus 1 minus maybe this one. Okay? So this is a bisection. So this fundamental domain has infinitely many faces, but it's very nice. So labeled by the point of each lattice. So each lattice has a rich geometry. So we can use geometry of each lattice. And roughly speaking, I think, for example, a Kummer 16-6 configuration sits in the each lattice. This is a main idea. Okay, I will explain soon. Okay, and then Both are used to Conway's theorem to study the hyperbolic reflection groups or hyperbolic lattice. And he described the structure of the orthogonal group by using this one. So maybe let R be this is a root lattice. A root lattice generated by some Leech roots. Generated by some Leech roots. And consider the orthogonal complement here. But root lattice, I mean negative definite. So each orthogonal complement has signature 1 positive and 25 minus rank R. So this is a Picard lattice of, looks like Picard lattice of K3. Okay, and both are showed first claim is projection of the wild vector into this is sorry, one more definition. So under the embedding, this embedding, we denote this is a restriction of the Conway polyhedron, Conway's fundamental domain to the positive cone here. Then projection of the wild vector is sitting this domain. So in particular, this is a non-empty. And number of faces. This is finite. Okay. Now consider the example. R is A3 plus A1. So this is 6 copies. Okay. And then orthogonal complement is isomorphic to the Picard lattice or the Picard general Kummer. Okay. And the projection, maybe the projection W. W is a hyperplane section. Optic model. And number of faces ds is, I forgot. Number of faces is 316. Sorry, I need water. And this 316 is divided into 32, 60 plus 192. And the first one, this is defined by minus 2 vectors. So the hyperplane perpendicular to this minus 2 vector. And the second one is a minus 1. Minus 3 over 4. So now you understand. So this minus 2 vectors, this forms a 66 configurations. So the 32 lines on the Kummer optic model. So we can identify 32 lines with this 32 minus 2 vectors. Okay? Then this 32 minus 1 vector. Each of them corresponds to projections, so 32 projections. And this is a 60 Geppel. And 192 Weber hexa. So this is a boundary of the ample cone. Yeah, this is a positive cone, X, but we have an ample cone, but infinitely many faces. But inside here, we have some finite polyhedron. And these are 32 minus 2. Of course, I cannot write down 32, but this boundary, common with the ample cone, that is a minus 2 faces. And other faces cut the ample cone, minus 1, minus 2. But it works, this, for example, projection works like a reflection with respect to this face. Okay? So each involution, like other reflections. And moreover, projection is a hyperplane section, sits in here. That's double. And any automorphism preserves the ample cone. So any automorphism sent to this projection of the Y vector sent to some point in the ample cone. But by using these involutions, this point coming here again. So finally, if you take any automorphism, and by composing these involutions, we get automorphisms of this finite polyhedron. And this automorphism group of finite polyhedron, this is isomorphic to S6 semi-direct G/2G phi. So this is the automorphism group. I explained linear action on the optic model. But this S6 cannot act on automorphism. This is the automorphism group of the YLSR points, but cannot realize automorphisms for Picard general K3. So this is a proof of over the complex numbers. Understandable? Very simple. And so today's main theorem is the same thing, more simpler. So the characteristic 2. We have only 4 singular points. Singular point degenerate to D4, but only one tetrahedron. So okay. Now I come to the characteristic 2. Okay. Okay. 2. So in this case, I consider the case ordinary. The most generic case. So the two-torsion group, this is a 2D2. And in this case, the equation of the Kummer quartic is known. This clear. plus xy. This is and it has 4 d4 singularities at coordinate point 0, 0, and it contains 4 tropes. Also, S contains 4 tropes defined by okay, so for example, hyperplane section x equal to 0, then remaining terms are all of the remaining terms are square. So the Mukai-san used Q, but we are working square is a square plus b square. So the x is equal to 0, then remaining are square. So that means that this is a conic equation, but square of the quadric. So that is a double conic. So this is a trope, 4 tropes. So this is a tetrahedron XYGT. Then this vertices are 4 rational double points, and each plane cut a double conic like this. So in this case, 16, 6 degenerate for 3. Okay, and also this surface has involutions, 8 involutions. So, for example, XYGT goes to YX, TG, and ZT, XY, and final one is a Cremona. So they generate a 2-elemental group of order 8. Kummer case, we have 2/5. Okay. And it's blowing up. In the case of over the complex numbers, the blowing up, the Kummer quartic is an octic model. That is a non-singular model of the Kummer quartic. But in this case, blow up, one times blow up gives us, so this is a D4. So one times blowing up, still 3 A1 singularities here. After blowing up, you get a D4 diagonal. Okay? Blowing up, this is a D4 diagonal. It's okay, like this. So blowing up, we get a octic model. Again, intersection of 3 quadrics. But it has 12 nodes. So configuration is like this. We have eight lines. So these are exceptional curves. So we blow up 4 vertices. And this part is a proper form of tropes. We have 4 tropes. And this is all of these are lines. Lines in P5. But still, in each line, we have 3 A1 singularities. These are A1, so totally 12 A1 singularities, 12 nodes. Okay. And then we take a minimal resolution. Then we blow up 12 times. So the totally 8 plus 12, 20 minus 2 curves here. And the dual graph, its dual graph is like this. Just a cube. Okay. And you can see, for example, here is a D4. D4, and here also. Contract of these 16 minus 2 curves, you get a Kotick model for D4 singularity. But you can contract different D4. That will go to dual. For example, this is an exception. So contract these 4 lines, we get a Kummer Kotick, this one. But also you can contract image of the tropes. Then you get another Kummer Kotick. That is a dual. Okay. And now, so this is a analog of the 16.6. So this case. And I take the root, maybe it's better. I take the root artist, R is equal to D4 plus D5, sitting in the 125, generated by some of these roots. Okay, then it's also a complement. This is from the Picard lattice of X. This is a minimal resolution. And then same terminology. So dx is a restriction of the cone wave fundamental domains to the positive cone of here. Okay, then dx has a in this case 38 faces, and of course this is decomposes 20 minus 2 faces, and 4 minus 1, 6 minus 1, and 8 minus 3 over 4. And Automorphism group, this polyhedron, this is nothing but a S3 G2G cube. So this group already appeared here, involution. Then, well, S3 appears naturally, so the character 0, hyperelliptic curve, genus 2, has a 6-point branch. So the S6 naturally acts. But character 2, this is only 3 branch points. So the permutation of the 3 points appeared here. So the and so the remaining problem is also we can identify this 20 minus 2 vector with this one. So the remaining problem is so to each face, so we should find involution, working like reflections. Then this gives us a generator of the Kummer, our Kummer. Okay. This is a story. But for example, I use this picture. Maybe I use a color. For example, let's take this one. Take minus one vector defined minus one face. Take then delta meet just two vertices. This antipodal. So we have four such a vector. Okay, and the remaining delta perpendicular contains which one? Oh, yeah. This one. Oh, okay, this one. You can see here D6 children. Okay. Oh, so sorry, complicated, but also here another D6 children, another D6 children, and more. Oh? No. Just a moment. This one and this one. Also, this one and this one. Perpendicular to, sorry, except two vertices. Sorry. But we have a D6 tilde here, and opposite side D6 tilde, two D6 tilde. This is a defined elliptic fibrillation on Kummer, and two sections. This is a section. We have two sections. But additionally, we have two roots, perpendicular. So this fibrillation is this one. Okay. And this elliptic fibrillation, model Bay group has rank 1. So the inversion of the model Bay group, inversion induces automorphism, involution on the Kummer, but it sends to delta to minus delta. So this is our involution. So other cases is completely same. In our case, to find a generator of automorphism groups, we can take a suitable elliptic fibrillation and consider the model Bay group. All of them have rank 1. And inversion sent to the generator, delta is the generator, and delta goes to minus delta. So delta goes to minus delta means delta is like this, perpendicular, this face, and it's sent to minus delta. So the like are reflections. So my claim is theorem. Theorem is in this case. So let this group generated inversions of elliptic fibrations, suitable, not, and then automorphism group or Kummer. This is isomorphic to G and to G cube. This is a theorem for the ordinary case. But the story works well all of other cases. And my time is still 5 or? Yes, yeah. And finally, I want to give a remark. So the extremal case, That is the case of product type. So the case Kummer in time itself. But here is ordinary. And F is a supersingular. And in this case, here is F and here is E. Then ordinary elliptic curve contains two torsion points, but supersingular only one, only zero. So the product case, on the product, we have two torsion points, okay? And then divided by the inversion, we get a Kummer surface, singular Kummer surface. But it contains three minus two curve, three non-singular rational curve, and two D8 singularities. So by taking the minimal resolution, we get the following 18 or 19 minus 2 curves. So take the minimal resolution. Then X contains, this is a dual graph. What is this? 8. This is a dual graph of 19 minus 2 curves. But Wimberg showed this, so I denote the lattice generated by these minus 2 vectors. Then also while group divided by this one, this is isomorphic to G over 2G. So that means if this lattice is realized as a Picard lattice of some K3, this K3 surface has finite automorphism group, okay? And it is known such a K3 over the complex number. But suddenly here in characteristic 2, this diagram appears. And as a corollary of Wimberg's theorem, our Kummer, automorphism group of Kummer, this is a finite. And this is isomorphic to 2G times SL2F3. So, and this is the automorphism group of the supersingular elliptic curve. So this is my final remark. Okay. Thank you.
Thank you very much. Question?
What's about the double cover of P1's 3 point? Could you explain?
You are co-author. Ramification branch point. Arching Schreier. Sorry. Sorry. Sorry, y square plus some ay equal x cube. Sorry, this term is 0. Then this is a square, sorry.
So in this product case, so you explain this at the end. So you get in characteristic 0 how many?
How many? It has a modular. It has a modular. This has a Picard number. This is a U plus very simple case, E8. This is a Picard lattice. So the transcendental is a U plus U. So the two-dimensional modular.
No, but how many different answers you have? There are the J invariants of the curves, yeah?
Oh?
Yeah. The J invariants of the elliptic curves, I suppose, play a role.
Yeah.
How many different answers do you get, depending on the J invariants?
I think all of them are same automorphism group. Because there are no correspondence here. This is the ordinary and supersingular, so no cycles. Anyone has the same Picard lattice, I think. カーネル。That is another problem. So, but usually a lot of vibration. So the image is almost all injection. But this case is not injection. So this is a kernel, numerically trivial automorphism. Yeah, that's right.
Do you have an explanation for the fact that these two groups have the same cardinal?
This group?
I think so. SL2 have 3 times the 2 and sigma.
That one?
This one and the one for.
But no relation, I think.
Okay.
All right, so thank you.
Yeah, thank you.